me clearly?
Yeah.
Good, thank you. First, thank the organizers for arranging this conference. It's my pleasure to have this opportunity to present some recent update about FEP to further improve the accuracy through enhanced sampling of water relaxation, ionization equilibrium, and protein conformational changes. Let's see how to press. Wait. Okay, good. As we all know, accurate calculation of protein binding affinity is of key importance in structure-based drug design. And over the past few years, we have worked on a number of new methods to further expand the domain of applicability of relative binding affinity FEP, as mentioned by previous speaker, including the co-hopping FEP, microcirculation perturbation, charge perturbations, and also the covalent inhibitors. In 2017, we spent another effort and collected FEP+ performance on a large number of data sets. Majority of them are prospective studies and also from customers as well. The summary of the performance showing here, we can see that for the vast majority of projects, the MUE is less than 1 kcal/mol in agreement with the accuracy seen in respective study. However, you can clearly see that for a small percent of cases, the MUE is much larger, approaching about 1.5 to about 2 kcal/mol, making it not very useful for lead optimization, where you have to differentiate the binding potency in a narrower binding affinity range. So what are the reasons for those outliers? So after a careful analysis about these outlier cases, we have identified 3 common reasons for FEP+ mispredictions. A, insufficient sampling of water relaxation in the binding pocket, as mentioned by many speakers in previous sections. B, improper assignment of the protein state in the ligand or in protein residue surrounding the binding pocket, or failure to account for the change of protein state during the binding process. For example, in the base 1 system showing here, the protein state of the ligand and this 2S residue in the binding pocket are coupled together. With a small R group modification here or heteroatom mutations in the ligand, it can change the preferred protein state of the ligand or in the protein residues. And the failure to account for those change of protein state can introduce large errors. C, insufficient sampling of protein conformation changes induced by ligand perturbation. For example, for the HEP90 system showing here, in the presence of smaller ligand, this part of protein close to binding pocket is adopting a looping conformation pointing towards the ligand. With a very small R group modification, introducing an additional 5-member ring, it pushes this part of the protein to adopt the helical conformation. The loop to helical conformation change cannot be sampled in the short FEP simulation, introducing errors. So over the past few years, we have been working on a number of methods to address those kind of challenges. So in the following, I'm going to present our effort. So about water relaxation. So water molecules are an integral part of the receptor. And during lead optimization, water molecules are often targeted for displacement to further improve the binding potency or selectivity. For example, for the HEP90 system shown here, the additional chemical group in the second molecule dramatically improved binding potency by displacing those water molecules in the buried pocket. However, as we know, the residence time of water molecules in deeply buried binding pocket can be very long, on the order of microseconds to milliseconds in sometimes. So the short FEP simulation cannot sample the exchange of water with box solution, introducing errors. And to address the water relaxation problem, we have implemented an enhanced sampling method called GCMC. I think some earlier speaker also mentioned this similar technology that is integrated with FEP+. So during GCMC, the water molecules inserted corresponding to entering into the binding pocket or deleted corresponding to exiting out the binding pocket according to the chemical potential certified detail balance condition. We have validated that our GCMC implementation can accurately and rapidly solvate the deeply buried binding pocket. The water molecules placed by GCMC match the crystal waters from the high resolution crystal structures. For example, we have looked at a number of systems, including HIV protease, PTP1B, bromine domain, HEP90, In all cases, water molecules are known to be important to explain the ligand SCR. And in all those systems, we perform GCMC simulations where water molecules are removed prior to simulation. And in a very short amount of sampling time, we were able to correctly place all those critical waters by GCMC. We also validated GCMC in the context of protein binding finish calculation. Here's one example. Receptor is HPP90. So it has 2 critical water in the binding pocket. Experimental SCR are available for few perturbations that introduce additional methyl group or additional fused ring to displace those water molecules. So we run FEP simulations on a number of systems, a number of ligands on the system. For example, from ligand 1 to ligand 2, additional methyl was introduced to displace the water. Ligands 3 and 4 have additional fused ring. Using the previous default FEP plus protocol without GCMC, see the results were not great. By comparison, using the GCMC enhanced FEP plus, the results get much improved. RMC is reduced to about 0.5 kcal/mol. We also confirm that GCMC is getting the correct result for the correct physical reasons. For example, for this perturbation between ligand 1 and ligand 2, adding this additional methyl group experimentally improved the binding potency by about 2 kcal/mol through displacing this additional water molecule. And GCMC is getting the correct position. So we can compare the GCMC results with the finish along the physical pathway. First, moving this water molecule from the binding pocket to bulk solution, followed by the ligand transformation. If the 2 results agree with each other, it proves that GCMC is getting the correct result for the correct physical reasons. This is exactly what we did here. So this is ligand 1 with 2 water molecules in the binding pocket. We first calculated the finish to move those 2 water molecules from the binding pocket to bulk solution. It was estimated to be about 7.6 kcal/mol. And then the finish to mutate from ligand 1 to ligand 2, introducing this additional methyl group in the presence of the dry binding pocket, was performed using NPT ensemble regular FEP. It was estimated to be 3.8 kcal/mol more stronger. This makes sense because the bigger ligand is occupying the vacuum region in the binding pocket. This also explains why regular FEP without GCMC is having trouble to explain the SCR for this series of ligands. And then we calculate the finish to move 1 water from bulk solution to the binding pocket in the presence of the bigger ligand. So adding the finish along the 3 steps in the physical pathway, it agrees very well with the GCMC perturbation from the direct perturbation from the 2 ligands, with hysteresis of only 0.05 kcal/mol. It should be noted that the calculations along the physical pathway are about more than 5 to 10 times more expensive than GCMC. So GCMC is getting the correct result for the correct physical reason and in a much more efficient way. So we have extensively validated GCMC on a very large data set, focusing on perturbations that displace water molecules. This includes 8 different protein systems, 76 ligands, and 139 perturbations. Each perturbation is either a modification that displaces a water molecule in the deeply buried binding pocket, like thrombin case shown here, or a perturbation that changes the interaction with the buried water, like the SD system shown here. So here are the results. So you run FEP both with and without GCMC on this data set. To test the sensitivity of results with respect to initial water placement, for each protocol, we run 2 simulations. One, retaining the crystal water in the binding pocket in the input structure. The other one, removing all the waters in the binding pocket. So the middle bars are the overall RMC using the regular NPT ensemble without GCMC, and the orange and the green ones are with GCMC, with 2 slightly different setups. So take-home message is very clear. So GCMC dramatically improved accuracy, reducing the overall RMC from about 2.3 to about 1.4. And if we exclude one HEP96 dataset that has very large experimental uncertainty, and also the SD system, which the ligand purine state is not sure, is not certain, the RMC using GCMC is about 1.2 kcal/mol. So this slide shows the per target performance using different protocols. We can clearly see that using NPT ensemble, so the results are very sensitive to the initial water placement. For example, for some systems like HP90 showing here, results including crystal water are much better. While for others, like for example, SD system, results removing the crystal water in the input is much better. By comparison, using GCMC, the results are almost identical with and without water. While improving the accuracy for perturbations that displace water molecules, we also confirm that GCMC is not introducing errors, introducing noise to other perturbations. For example, the GCMC results on the JAX publication are comparable to that with NPT ensemble. So another second topic about the ionization equilibrium of protein on the ligand. We all know that the biological systems we are interested in contain many titratable residues with pK close to 7. In experiment, those titratable residues, both the protonated and deprotonated form at equilibrium. However, in classical MD simulations, we can only simulate a fixed protonated state. And if for systems, well, it's not clear what the preferred protonated state is, we have to consider all the possible protonated states and weigh them according to their finish. Otherwise, the finished results will not be accurate. For example, for the KSP system shown here, for a number of ligands that introduce additional chemical group on this R vector, the experimental pK of those ligands range between 5.2 to 10.3. So for 87, at pH equals 7, the neutral form is dominated, while for 85, the charge form is dominant. For the other two ligands, both neutral and charge form have equal contribution in solution. So if we don't consider the ionization equilibrium of ligands, for example, if we only model the neutral form ligands, the FEP results were not great, particularly for the perturbation between 85 and 87, there's large errors because the preferred protonated state of two ligands differ in solution. And for the same reason, if we only model the charge form ligands, there are also large errors. So to take into account the ionization equilibrium of ligands in solution and in protein binding pocket, we have implemented the pK correction method in FEP+. So apply pK correction method, we need to run FEP simulations between neutral form of the ligands, between charge form ligands, and also a few perturbations collecting the neutral and the charge form to form a closed cycle. And from the simulations, we can obtain the shift of pKa on the ligand due to the protein environment. Combining the pK of ligand in solution, we can rigorously calculate the relative population between neutral and charge form ligand in the binding pocket and in solution, and obtain the final pK corrected relative binding finish. So here's the results. After pK correction, the results get much improved. So for systems with one or two uncertain titratable residues, we can use the pK correction method as mentioned. However, for many other systems, like the base 1 system I mentioned earlier, the titratable residues, the protonated state might be coupled together. So we can still use charge FEP to calculate the finish difference between different protonated states. However, as we can see here, the number of possible protonated states scales exponentially with number of titratable residues. And for three residues, there are 8 different protein states. And for bigger systems like protein-protein binding, it's almost impossible to enumerate all the possible protein states and calculate finish. So the more general way to address this issue is the constant pH method. So constant pH method allows all the possible protein states to be modeled simultaneously in one simulation. It has the potential to significantly improve the accuracy for those kind of systems where the protein state for the ligand and the protein coupled together. And also it's very important for protein-protein binding. And furthermore, as mentioned earlier, a large portion of FEP+ mispredictions is due to the incorrect protein assignment. So constant pH simulation is the only way to make FEP calculations robust to errors in the input protein ligand structures. So over the past few years, we have been working on general method, general constant pH method in Desmond backend that will be integrated with FEP+. So to validate constant pH, we have collected a large data set, including 12 proteins, 112 titratable asp and glue residues with experimentally measured pKa. So first, we use the current available protein residue mutation FEP to calculate pKa. Using the default OPS3E force field, the initial results were not great. So we find that OPS3E tends to overestimate the stability of the neutral form. So RMSE is 2.4. So through a lot of effort, including taking into account the coupled titratable residues by carefully assigning the protein state for surrounding residues and also by input force field, particularly for the better solvation model, which I think can also address the one of the outlier that the previous speaker mentioned, while introducing a bigger chemical group in the solid exposed region, FEP overestimate the binding potency. And also we have improved the torsion parameters for the neutral form of asp glue. We were able to dramatically improve the accuracy of pK calculation, reducing the RMSE to about 1.2 gigaball. Similar accuracy is also obtained for histidine pK calculations. And this provides a solid foundation for constant pH methods development. So as of now, we just have some validation for constant pH method we implemented. For example, for titratable asp in the protein binding pocket that forms a salt bridge and hydrogen bonding with the surrounding residues. Experimentally, the pK is strongly shifted to favor the charged form, which is accurately calculated by FEP. And we also ran constant pH, and we obtained the fraction of deprotonated form as function of pH and fit this curve by Hill function to obtain the pK estimate. The pK from constant pH estimation also agree well with the benchmark FEP. So here the result is using the OPS3E. OPS3E, again here, overestimate the shift, but the results with the newer version of force field to be released will be much better. Another example, we also perform constant pH to calculate the pK of these 4 titratable residues simultaneously in one simulation. And our constant pH results also agree very well with our chemical FEP and also with experiment. One interesting finding here is that the ionic strengths in solution have a large effect on the pK results. So from constant pH, we run 2 sets of simulation. The first set without additional salts, the second set with additional salts. The results with additional salts matching experimental condition or matching FEP simulation condition will have much better agreement with both FEP and with experiment. And we expect the integration of constant pH with FEP+ to be released next year. So in the last few minutes, I'm going to briefly talk about an ongoing research effort to try to calculate the protein conformational energies. So I will use the HB90 example mentioned earlier to explain why this is important for protein ligand bonding. So as to recap, for the smaller ligand, this part of protein prefers the looping conformation, while for the bigger ligand, it pushes the looping to adopt the helical conformation. So for the perturbation between the smaller ligand to the bigger ligand, if we use the looping conformation protein to run this FEP, because the bigger ligand has severe stereo clash with the looping and the simulation crashed. Even if it does not crash, the bigger ligand will be predicted to bind much, much weaker because of the stereo clash. By comparison, if we use the helical conformation protein, the bigger ligand is predicted to bind much, much stronger than the smaller ligand, a severe over-prediction as compared to experiment. So FEP results are very sensitive in this kind of situations to the input protein conformation, and none of them is very accurate. The reason is very clear. So the FEP results using the looping conformation is missing the finish to reorganize the protein from looping to the helical conformation in the presence of bigger ligand, while the FEP results using the helical conformation protein is missing the component to reorganize the protein from the helical conformation to the looping conformation in the presence of smaller ligand. And the finish associated with these 2 vertical processes are called protein conformation finishes. That is the phase difference between the different conformations of same protein in the absence of ligand or in the presence of different ligands. So I just want to mention that ligand-induced protein conformation change is very common. In addition to HB90, by searching from PDB, you can find many examples. The famous one include the P-loop motions in kinase or the DFG-in to DFG-out conformation changes in the kinases with type 1 and type 2 inhibitor bind. The calculation of protein conformation phenotype has many important applications. First, obviously, it can expand domain of applicability to enable scoring of ligands that binds to different conformation protein, like the HB90 example mentioned earlier. Furthermore, it might help to identify and validate low energy conformations that is not observed in crystal structures, like cryptic pocket or allosteric pocket, and enable structure-based drug design on those lower conformations. In addition, if the different conformations of protein are associated with different single transduction pathways, then by predicting which conformation each ligand can stabilize, we might be able to predict the functional response due to ligand binding. Say, for example, whether ligand is agonist, antagonist, or inverse agonist. And it also can help to select best structures from homology modeling or from induced fit docking. So due to limited time, I'm not going to talk too much on the technical details and methods. I'm going to present some proof of concept results for the initial studies. So back to the HB90 example. So using the helical conformation of protein from the smaller ligand to the bigger ligand, FEP predicts 6 kPa stronger binding of the bigger ligand, a severe over prediction as compared to experiment. And then we applied protein conformation FEP to calculate the phase difference between the loop-in and helical conformation protein in the presence of smaller ligand. And the loop-in conformation is predicted to be favored by about 2.6 kPa. Adding together the ligand perturbation, the results agree very well with experiment, -3.4 versus -3.2 in experiment. We have also been trying to use protein conformation FEP to explore the kinase conformational landscapes. For example, here is the able kinase with 2 different ligand binds. The P-loop adopted very different conformations. So according to W score, a method developed by Professor Rich Frinsner and coworkers that takes into account the different conformation protein along with their state penalty, it suggests that 2A7A loop has about 4.5 kPa more favorable phenotype as compared to QOH. And using protein conformation FEP through different setups, we consistently get the same results that the 2A7A loop is more favorable by about 3.5 to 5 kPa in very good agreement with W score estimate. Similarly, we have also applied protein conformation FEP to try to calculate the phase difference between the DFG-in and the DFG-out conformation of able kinase. So this involves a very large perturbation, including more than 12 residues in the alchemical region. So due to limited time, I'm not going to go through all the details, just make a very long story short. So here we find a very strong coupling between the protonation state of the DFG motif and the DFG conformation changes. In particular, we find that in the DFG conformation, the asp should be preferring the charged form, while the DFG out conformation asp should be preferring the neutral form. And depending on whether the asp is neutral and charged, the phase landscape of the DFG and the DFG out are very different. So combining with protein conformation FEP and the PK calculations, we conclude that in the DFG conformation, the asp should be charged, while in the DFG out conformation, asp should be neutral. And the neutral form of asp in the DFG out conformation has about 0.5 to about 2.5 kPa more favorable phenotype as compared to DFG with the charged form of asp for the able kinase. So summary, so through analysis of aggregate of class data, we have identified 3 common reasons for mispredictions, including insufficient sampling of water relaxation, lack of accounting for the ionization equilibrium of titratable residues, and also the insufficient sampling of protein conformation changes. So over the past few years, we have worked out a number of methods to address these problems, including, for example, to enhance the sampling of water relaxation. We have developed GCMC that is integrated with FEP+, and obtained much more accurate results, particularly for perturbations that displace water molecules in deep barrier binding pocket. And also we have implemented the pK correction method and working on the general constant pH method to address the issue of protonation assignment. And also we are working on lower method to calculate the protein conformation finishes. With this, I'd like to acknowledge all those people who have contributed to this project. In particular, Greg, Wei, and Mikolai are the main contributors to the projects I just mentioned. And thank you all for your attention.
Great, thank you, Lingle. That was a very good talk. We have a little bit of time for a couple of questions. So the first question comes from Christopher McClandon. He asks, can you elaborate on how the protein conformational FEP method captures the protein reorganizational free energy? Is it something like metadynamics between the two states?
Actually, no. So previously, people have tried using metadynamics or ambient sampling to calculate the different conformations of biomolecules, but all those methods require a reaction coordinate or a physical pathway to collect different physical states. The reaction coordinate is very kind of difficult to select and it's system dependent. So we want to avoid those methods. So in our method, it's kind of extension of the co-hopping or macrocycle FEP. Well, we introduce 2 copies of the loop in different conformations to construct a mixed topology protein. So you can think about this as a really big co-hopping FEP, where the core of the perturbation is the entire protein except the loop in different conformations. And the loop in different conformations are in the alchemical region. Yeah, this is on a very high level how protein conformation FEP method work. I don't have time to go through details in the presentation. Sorry for that.
Of course, yeah. Actually, so personal question. So it sounds like you can only use this on systems where you know there's a conformational change. Can you use it on a system where there's, if you're not sure if there's a conformational change?
Yeah, so currently the method only works to calculate the difference between different conformations that you identified either by experiment crystal structures or through other methods. For example, for prime, the loop prediction method, you can, if you design a ligand that has severe clash with existing crystal structure, and then you can try using a loop prediction, say, is there an alternative loop that can adopt a new ligand? And then we can use protein FEP to calculate the difference between the current conformation and like a predicted conformation by some other methods.
Perfect.
Yeah, same as relative binding affinity FEP, we can use that to evaluate, score new design ideas, but it's not a tool to design new compounds. Yeah.
Okay, perfect. Thank you. Michael Gilson, one of our panelists, asks, can you say a few words about how the constant pH method works, and in particular, how you get a significant acceptance rate for protonation state changes?
Yeah, so we are implementing the lambda dynamics approach. So the way how it works that you introduce an additional lambda variable for each tetrahedral residue, and then you have the potential of mean force between the deprotonated and protonated form of that residue in solution, and then you fit that potential mean force in the complex formulation as well, so that you reduce the energy barrier between the protonated and deprotonated form, and also you try to avoid something in the intermediate state that doesn't correspond to any physical endpoints.
Perfect, thanks. And then a related question from Ernest. He says, really great talk, really enjoyed it. Have you employed your constant pH molecular dynamics protocol to calculate the pKa's of cysteine residues? Catalytic cysteine pKa's have proven difficult to compute via conventional pK methods.
Yeah, so that's on our list. So right now we are focusing on the histidine asp glue, and those because those are most common for drug design applications. But we're also working on other like uncommon residues like cysteine just mentioned. Also lysine in some cases also have the neutral form. That's on our to-do list.
Perfect. Thank you so much. So Lingle, there's a number of questions which we don't have time to continue to go through live, but if you'd like to answer those during our next talk, that would be much appreciated. Thank you for your great talk, and we'll transition to our next speaker. So we'll now have the privilege to hear